Thank you, Rajat, for the kind introduction. And thank you, ARC and Cecilia, for hosting me today. So as you can gather from Rajat's introduction, everyone calls me TJ, even my kids, so please do the same. One thing that I need to correct in Rajat's introduction, though, is we're no longer operating as University of Adelaide. We're now Adelaide University, which is formed from the merger between two very big universities in the state of South Australia. So the University of Adelaide and University of South Australia. Now we are 23 days into operating as Adelaide University. Fingers crossed. So far, so good. Okay. Within Adelaide University, I'm part of the Australian Institute for Machine Learning. And within this institute, I lead the AI for Space group, as Rajat mentioned. Okay, so a bit of an introduction to the group. It's, the screen, I'm blocking the screen actually. Is that how it usually works? Should I stand by the side or this is okay? Is that all right? Okay. So we have a moderate-sized group, and these photos just shows you, I guess, the beautiful sights and scenes in Adelaide, in South Australia. And the work that will be presented today is mostly due to the faces that are highlighted here, mostly Jawed, Ethan Elms, Tam Nguyen, and Marcus Martins. Marcus is no longer with us. He has left us to take up an associate professorship at Tokyo Institute of Technology, which is an amazing accomplishment for Marcus and the group. Okay, so we're the AI for Space group. I'd like to define what that means, because when I say AI for Space, people think about LLMs and ChatGPT in space, and we're actually trying to do that as well. But we started off having a different interpretation of AI. And this is based on the idea that we have a platform in space somewhere, could be on a planetary body, having an onboard computer with sensors and communications components, which pulls in data from various sources. It could be the environment itself. It could be other machines in the environment. It could be information relayed from ground. It could be information housekeeping data accumulated on board. We'd store the data, process them using the AI algorithms that we're familiar with. By AI here, it could be machine learning, computer vision, robotics, mathematical optimization. And then very importantly, we decide what to do next based on that understanding of the state of the object, the state of the system, and the environment in which it's in, and then execute those actions. All right? In a space context, you're wondering what actions are possible. I think maybe in the context of a rover, it's more obvious. You want to move to avoid a rock. In a case of a satellite, it might be less obvious, but there are things you can do on a satellite that may not even need to involve maneuvers. So, for example, reorienting the satellite so that you point your sensor at a different location, or maybe just send a distress signal because you're about to be colliding with another space object. Right? And these actions change the next set of data that you get. So I ripped this off from Russell and Norvik's definition of AI, because I taught that course starting 10 years ago. This is what I mean by AI when I say AI for space. So one level of detail down, where do we execute this AI for space vision? We do it on onboard processing and decision making, onboard satellites and space systems. We do it on GNC, guidance, navigation, control of space systems. We do space robotics as well, and we also do downstream processing of space-derived data. This could be lots and lots of Earth observation data, or data of cameras pointing up, looking at things in space. So a few examples of where we apply AI for space. There's an increasing emphasis on processing Earth observation data on board satellites, and we successfully demonstrated a geospatial foundation model in space, and we did it through a couple of channels. One is a Canini which is a South Australian government-funded Earth observation mission, which has an onboard neural network accelerator. And we also did it with the Bartholomew payload. Not the Bartholomew payload, the Bartholomew module in the ISS, and there's a payload on board with an onboard computer, which is an ARM-based system, and that's facilitated through Thales Alenia Space, and with a kind facilitation by ESA. So why do we want to put a geospatial foundation model on board? We process it so that we get insights that we need on board, rather than downlinking all the data and then send it to a data center. If we get the insights on board, then the satellite system just needs to send you a text message. I see flooding in Indonesia, for example, rather than sending you tons of images, which you then have to process later. And there are other kinds of applications you can think of that will benefit from this reduced communication bottleneck. We apply our ideas in onboard perception for on-orbit servicing. So we hopefully will have a chance of demonstrating this in a orbital servicing mission funded by the Australian Space Agency, which is a joint collaboration, a joint mission between ISRO-led, but several Indian companies and Australian companies and research organizations such as my group here. So the role of my group will be to develop algorithms that can perform satellite pose estimation, which is a topic that I'll go more deeply into later. So we're also affected by the same thing that is affecting you, which is the readiness of the ISRO launches. Another example of where we apply our concept is in lunar exploration as well. Here we're collaborating with a consortium in Japan to map the subsurface of the moon for water elements. My group's role is developing the vision algorithms, the AI algorithms that help figure out the position of the satellite as it's orbiting the moon. Okay, so that's just the introduction to the group. Now into the topic of the talk. You could recall, therefore, in this AI for space concept there, perception has a role to play. Let's go into that. So this is a real footage of a rendezvous and proximity operations. Probably one of the Soyuz spacecraft docking with the ISS, right? So this is a real footage that anyone can pull off from YouTube, by the way. So if I play the sound, is there sound maybe? If I play the sound, you'll hear human operators talking to each other. You know, move it to the left, move it to the right, orient it differently. So, so this is how rendezvous and docking is done at the moment. But we're moving into an age of space utilization that is leaner, more commercially driven, and more open to taking risks. And that involves putting more autonomy in these operations. But what business can you build out of this? This is information I retrieved in 2023. It's already old information, but you've got companies looking at satellite mission extension as a business. So your satellite, your expensive communication satellite is running out of fuel, or it's suffering from a form of malfunction. You want to send another satellite to go up to it to repair and extend its lifetime so that you can keep the orbital slot. Okay? This is actually a business, right? And there are already a few companies doing that. The big companies are doing that. The smaller companies, such as Astroscale from Japan, is doing that as well. And there's refueling, there's maintenance, there's even basic things like inspection, which is what we're trying to do in our own mission. The joint India-Australia one that I told you previously, led by Space Machines Company, an Australian startup. So when you get startups involved in doing this, you don't have the same budget as space agencies. You can't have a room full of mission operators like this managing every single mission because you run out of money before you make money. So I believe autonomy has a big part to play, and within that, in a specific application context like this, we want to do spacecraft perception. Why do we need spacecraft perception? I did mention GNC, guidance, navigation, control, as a theme of the group, and here spacecraft perception is used to figure out how to essentially get close to each other in orbit so that you can interact. Two spacecraft can interact with each other. The bottom left image you see is an actual footage taken in geostationary orbit using an infrared camera. That was the first time it has been demonstrated that we can rendezvous with an older satellite that was never designed for docking and rendezvous. That was the first time. The ISS example I showed you earlier, obviously from the beginning it's designed for docking operations, but the one on the bottom left, achieved by Northrop Grumman, was the first time where it was demonstrated you can rendezvous with a passive, maybe dead object. Okay, so what do you need to know about the passive dead object so that you can rendezvous with it? It's not me who said we need this, but countless of papers have been written by the aerospace, astronautical people. We need to figure out the pose of the target object, all right? If both satellites are operational and want to collaboratively dock with each other, I'd say flash some light in some pattern to allow the chaser satellite to figure out your pose, or show a 2D barcode. But if the target satellite wasn't designed to do this from the beginning, and it's already up in space, and you want to rendezvous with it, what do? The chaser will have to estimate the pose by itself from sensor data. And that's where spacecraft perception comes in. So let's define a bit what we mean by target pose. It's very standard. If you've done a computer vision course or a robotic vision course, you'd know this already. All I'm doing is just translating it to the space context, right? So you've got a camera, maybe on a selfie stick extending from your chaser satellite, looking at a target object. This could be a CubeSat in space that's already non-functional because the undergrad student who built it introduced a bug or something, who knows, right? It's a piece of junk in space. You need to figure out its pose. What do we mean by pose? Take a picture of the target object, and we ask, what is a rigid transformation from the object frame to the camera frame? Okay, so that R and T there is the pose that we're talking about. The position of the object relative to the camera, and the orientation as well of the object relative to the camera. Okay, so the implicit assumption here is that you know the shape of the object, and I guess for many of the cases that we're interested in, we do know the target object because we are the ones who sent it to space. It's just that it's now dead, and it needs maintenance or it needs fuel extension, and we want to rendezvous with it, right? So all I'm saying is, it's for many applications, it's valid to assume that we know the target object. What we don't know is, right there on the spot when we're getting close to it, what is the pose of the target object relative to the camera? So then the pose estimation method, which is a spacecraft perception problem, takes that image, then estimates the pose with input as well of the known target shape. That is what we mean by when we say object pose estimation. Okay, so what are the techniques that we can apply to solve this problem? There's plenty of techniques we can borrow from the computer vision literature or the AI literature. Object pose estimation is a very, very established topic in computer vision. If some of you are computer vision researchers or robotics researchers, you might have encountered this problem already, right? It's used a lot in grasping and manipulation, before a robot manipulator interacts with the target object, you need to know where it is and how it's oriented with respect to the camera of the robot. Okay, so it is an equivalent. Sorry, not even equivalent. It's the same problem except that we're doing it in space. I'll step through a few paradigms for doing this because there's way too many methods out there and it's not possible to cover them, although there are good survey papers on object pose estimation. Pre-deep learning would be using SFM and SLAM. Firstly, we assume we have, if we don't have the CAD model, we assume that we at least can take lots of pictures of the target object, use structure for motion or SLAM to reconstruct the point cloud of the target object. So that's like the offline phase. And then in the online phase, camera takes a picture of the target object. We do key point detection and matching between that image and the offline images that we've taken. We get a set of essentially 2D, 3D correspondences from that process, and then we perform what's called a perspective endpoint solve a perspective endpoint problem to get the target pose. So pre-deep learning, again, a lot of the key point detection and matching is done by using classical methods, such as the ones you see here. I call it a key point because these are interest points that appear to be salient to the algorithm, right? The handcrafted algorithm decides, but you can't predict beforehand, or you can't even direct where that key point should be. It depends on that image. So entering the deep learning phase, deep learning era, naturally people looked at end-to-end learning as a start. Image goes in, goes through some regression network, and you output the pose directly. Okay? It's a valid approach, which is quite successful as well. And again, I don't want to go into the detail of what are the major pose regression networks because there's so many of them. Just step through the major ideas. A hybrid approach or a hybrid paradigm would be to combine, the deep learning with the classical approach, whereby you use the deep learning for what it's good at, which is to deal with the front end, the image, takes the image in, estimates predetermined landmarks on the target object. Okay? Notice I've changed from key point to landmark. Key point, you can't predict beforehand what you want to find. It depends on the image you get. In the landmark, these are pre-identified features on the object that the human has determined to be somehow useful. And so you train the landmark regressor to find these specific number of points. And then that essentially produces a 2D, 3D correspondence set on which you apply perspective endpoint to get the pose. So more detail about this hybrid approach. We'll keep coming back to this figure before. This is the method we proposed for the 2019 pose estimation, satellite pose estimation challenge organized by Advanced Concepts team at ESA. We won that challenge. So it's a very standard computer vision approach. Input image comes in, crop and resize it. Well, firstly, we detect it using a standard object detector. I think back then, some YOLO variant was popular. Detect it, crop it, and then the landmark regression gives us the 2D landmark. We train the landmark regression to always find these number of landmarks, and these landmarks correspond to these 3D points on the CAD model. Okay, so again, these are landmarks, not key points, because we have pre-identified that these are the points on the object we want to look for. Okay, so the landmark regression essentially gives us the 2D, 3D correspondences. Then we go through the P&P again to get the target pose. This multi-view triangulation bit is offline, and it's optional if you have the CAD model. In the challenge, because we weren't given the CAD model, we had to do multi-view triangulation, which is a fancier way of saying structure from motion to estimate this 3D object from the images. But it's offline anyway. So the workhorse of a pipeline like this would be the landmark regressor. And we used, back then, state-of-the-art HRNet, essentially combining high-resolution feature maps and low-resolution feature maps to predict those landmarks that we're interested in. So yeah, so just another viewpoint of the same thing. I guess this page is to emphasize that after that landmark regression, you'll have some optimization here to get the pose. And this is the essence of this hybrid method here. Okay, so this worked quite well. We won a couple of challenges based on hybrid methods like this. So coming back to the topic for today, why neuromorphic? Okay. Prior to this stage in this talk, haven't really talked anything about neuromorphic yet. So we should talk about what is neuromorphic first, right? Maybe not everyone here knows what neuromorphic means, but the word itself essentially means bio-inspired, inspired by living systems, rather than designed from scratch by humans, right? Taking inspiration from nature. That's what neuromorphic essentially means, okay? In engineering, probably that's too general, but in robotics and vision and AI so far, there's a couple of ways where neuromorphic ideas, neuromorphic technologies have taken hold. One of them is neuromorphic sensing. Okay, some of you might have encountered this before. So this image, this diagram contrasts a normal frame-based camera with a neuromorphic camera. So a frame-based camera is a camera that you have on your phone where, at a very high frame rate, maybe it gives you a picture which you can then combine into a video. In a neuromorphic sensor, instead of taking pictures, every pixel operates independently, sensing change. I might be talking about stuff that, would the students know about this kind of thing, or it's worthwhile to go through these basics? Okay, so I don't have to talk about these really basic stuff. Okay, so neuromorphic sensor is technology that is being considered for spacecraft perception. Neuromorphic computing as well is what we're trying to get into. Just briefly, so that we know the high-level idea, unlike the usual computer that we work with, which is based on the von Neumann architecture, maybe 100 years old, a neuromorphic architecture, it's massively parallel, you co-locate processing and memory, and the program that runs on a neuromorphic chip is a spiking neural network. So these are basic units of computation, where the inputs, outputs are in the form of spikes. It looks very much like a normal neuron that you have in a deep network, but the basic fundamental difference being that the input and output are spikes or events. When it's implemented in hardware, such as in a Loihi 2 neuromorphic chip, each unit of computation would go through these blocks, and each of these blocks would have its own instruction set that determines the sort of operations that are possible. And each neuron, each unit of computation, which is called a spiking neuron, in theory operate independently of the other ones. Just like in the neuromorphic sensing case, each pixel operates independently. Sorry, can you repeat the question? No. That might be a good business idea to come up with a neuromorphic sensor that has a neuromorphic processor inside. Maybe someone's already doing it. But as a concept, these are different concepts. Correct. That is a perception, that is a sensor, and this one's the processor. Okay? But both are neuromorphic because they share this similarity that it's spike-driven, it's asynchronous. Good question. Okay, so what is neuromorphic? We've covered it. Two main things, sensing and processing. Why do we want to do it in space? YouTube has tons of videos like this that gives you ideas, how to drive your research. So the main challenge that we need to deal with is a harsh lighting condition. What do I mean by that? This video is too slow. This is what I mean. Okay, why does it look like that? The contrast is bad. Yeah, why is there overexposure? Yeah, that's what glare means. But why do we get glare? And there's no atmosphere to diffuse the sun, right? And also, not to mention, these space objects are made from metallic things that are shiny. Okay, so that will happen. Here's another example. Look at that, poor contrast. The sun is in the background, and with a normal camera, you're starting to lose detail on the target that you might want to rendezvous with. And these funny colors as well. All right, real footage from space. I didn't cook this up in my lab. And these things are very hard to simulate in software, by the way. These lighting effects are very difficult to simulate in software. Another example, you don't see any detail on that satellite there, on that spacecraft there. 3 astronauts on board guiding it. You run out of budget if you use 3 astronauts on board to do your on-orbit servicing company. Okay, so it's glare, yes. Yeah, because you can't see it. There's no signal. Like if you train your neural network to look at objects with textures, but in space, this is what you get. You lose the detail you need for the neural network. Another one, less obvious, but you get occasions like this when the Earth is in the background and the Earth is very bright because it's obviously diffusing, receiving sunlight and then diffusing it all over the atmosphere. And the part I want to get to is this. Now you have a very bright object in front of an even brighter background, and you're supposed to dock with that, right? Again, a poor contrast scenario. Okay, so why neuromorphic? Why neuromorphic sensing in particular? We had this hunch that because of this bio-inspired nature of neuromorphic sensing, which allows it to have a really high dynamic range, it's about 120 decibels compared to 50 or 60 decibels of a normal camera. And because these things go up exponentially, we're talking about millions of intensity levels, minute intensity differences that a neuromorphic sensor can tell apart that a normal RGB camera cannot. Okay? So to prove this point, we set this up in our lab. Essentially, firstly, we have the target objects, which are made to look as metallic as possible because satellites and spacecraft tend to be metallic. The solar panel, for example, already is very metallic, right? But our main sensor here, main apparatus here is a beam splitter, which is a prism that is housed in this casing here. And we have 2 cameras that is receiving light that is split by the beam splitter. One camera is an event camera, the other one is a normal RGB camera. What we want to do here is to use this setup to look at an object like that. This is in our lab. Using the beam splitter, we exactly align pixel by pixel alignment between the RGB and the event camera or the neuromorphic camera. And this proves our point that using a neuromorphic sensor, you can see details where the RGB cannot see. Okay, so that answers the first question, why neuromorphic addresses the first challenge of harsh lighting. The second challenge that we'd like to solve is very hard compute constraints that is imposed on space systems, right? So what do I mean by very hard? Traditionally, for these big budget missions, such as the Perseverance rover, which takes a lot of time to develop, decades even, engineers are very, very conservative. They tend to stick to things that they know work well. So on Perseverance today, humanity's greatest explorer on Mars so far, it's running on a PowerPC of that era, 110 megahertz to 200 megahertz, one core, tiny cache, and draws about 10 watts. You can't run your deep learning on that. Things have started to change, so maybe not for the big ticket missions yet, but increasingly cheaper missions for various purposes, Earth observation, communications, whatever. You can now get payloads that incorporate NVIDIA Jetson devices. Okay, so this is from our, one of our industry collaborators, Infinity Avionics, where you can buy space-qualified payloads, that space-ready payloads that include NVIDIA processors. So Jetson Orion NX is much more powerful than that, but still, it draws 25 watts. Is that a good number? 25 watts? It's a poor number. Every time I suggest to a satellite company, do this NVIDIA thing so that I can run my deep network, the first thing they ask you, what is the power, right? 25 watts is hard to sell. They want to keep this as low as possible. So even though the compute power capability has increased, we're still dealing with power constraints. Okay, so that's where we think neuromorphic computing can help, because as I'll show you later, due to its asynchronous nature, the power draw is a tiny fraction of that to solve the same problem. Okay, so here's our attempt at pulling in everything we know to build an end-to-end neuromorphic spacecraft post-estimation pipeline. This is what we started with, which is a traditional RGB and deep learning type paradigm. Where do we do the neuromorphic? The obvious one is, let's change the sensor. Okay, that's easy to do, and we've done that a few times. All we did was to convert the event data into event frames, and then we process it using the pipeline that we're familiar with, and it works, right? So nothing much to talk about here. Then we looked at, there's still remaining domain gap between the synthetic data we use to train synthetic event frames we use to train the network and the real event frame that we get in practice. So with Rajat in his previous life, we developed a test time certifiable method to iteratively improve the landmark regressor during inference time. Won't go into the detail because not the focus of the talk anyway to go into details. And then we looked at fusing RGB and event because yes, the event frames will be more robust to these glare situations, but we envision there are situations when the relative motion between the camera and the object is low. The noise level in the event sensor will be very high. On the other hand, the RGB does not care about low relative motion, so there's its strength there. It would be great to fuse the RGB and the event so that we can leverage their relative strengths. If you ask me what if there's glare and low relative motion, then we can't do anything. But at least, yes? Yeah, so in practice, nothing is ever perfectly static in space. Everything has relative motion. So I don't think in practice this will be a problem, but this is one thing we said in the paper, that, this is why do we need fusion? So that it's not only the event camera fixing the problem with the RGB, but RGB maybe can also fix the problem with the event camera.
So suggesting we can just in the satellite, we have the event camera and we have a motor on it. It's if it's too stable, we'll just start spinning the camera.
You have to talk to the satellite builders if they want to add a motor just for you to turn the camera. I think most satellite builders want to avoid moving things or unnecessary moving parts on a satellite. But in real life, I think when you orbit around each other, there won't be situations where you're completely relatively static. So there'll always be relative motion. Oh, we haven't got to that part yet. So, so this is the result proving the point that if you train the pose estimator on the RGB only, it will be bad when the glare shows up, because the domain gap that it has never seen in the training data. It's very hard to simulate glare in Blender, for example, because you need to know material detail, you need to know the lighting accurately. Very hard to simulate. Whereas in the neuromorphic frame or the event frames, it doesn't get perturbed at all. So when you fuse them, then when you fuse them, then they have the exact same results, and then both are stable. So yeah, this is just numerical values showing that in the RGB, when you have glare, then the error goes up. In the event only, when you have low relative motion, the signal to noise ratio reduces, so you have the pose error goes up as well. If you fuse them, then both are generally okay. Left column is the position error, the right column is the orientation error, and you see similar trajectories. Okay, so that's replacing the sensor with the neuromorphic. And coming back to your question, where is the spiking neural network? Let's do the landmark regression and object detection. We haven't done a lot here. We've mainly taken existing stuff, specifically spiking ResNets. There are spiking versions of ResNets that we have repurposed to do landmark regression. So in a broad sense, during inference, we would input J time sequential event frames. It outputs J sequential regression outputs. We take the last one because, we need to wait for information to accumulate in the spiking neural network, in the spiking ResNet, and before we are sure that the result has accumulated all the information it needs from all the input data. We applied standard things here. It didn't work as well as the RGB deep learning counterpart, but that's the starting point. The object detection, we also applied standard spiking object detection.
So how about the energy consumption? As you say, like animals to save energy, right?
I'll get to that part.
Okay. And then for side, like sensor side and
So the sensor side already by design, you can look at the spec sheet.
yeah, so
If you believe the spec sheet, it's 100 times different or something like that.
100 times smaller than
Yeah. That's what the manufacturer claims. On the sensor side, we didn't measure. But the story is not complete yet. The last part, which is the post-estimation. And that was the tricky part, because if we want to take this two-stage approach, that second part is an optimization problem, not a learning problem. You can't just throw a spiking ResNet at it. So we had to relook the perspective endpoint problem, which is traditionally solved as a nonlinear least squares problem. Can also be solved by direct linear transformation, very classical multi-view geometry technique where we linearize the constraints, the post constraints, and then solve algebraic least squares using singular value decomposition. Neither of these are applicable in a spiking neural network because the instruction set will not give you an SVD. The instruction set will not support a simple differentiation to give you gradients in nonlinear least squares. So what did we do? We looked at a very old method to do DLT with this, which is inverse iteration. And all it's doing is solving linear least squares iteratively and renormalizing the pose vector so that we respect the unit norm of the SVD. Long story short, I don't want to go into the detail. This linear least squares that we solve can be posed as a quadratic optimization problem, which admits neuronal dynamics that allow us to implement it on the spiking neural network. That allows us essentially to pose perspective endpoint as a spiking neuron. I am skipping a lot of steps here because practical neuromorphic chips are still very restricted in many ways. Instruction set for one, numerical precision being the other as well. So all the data points have to be either integral or binary. How do you use that to solve for pose, which is a continuous manifold constraint object? Lots of the things need to be done, but we managed to do it. Your point about power. just looking at the PNP solving alone, the post-regression, also the landmark regression, because we're just using spiking ResNets, there are other results in other papers already, which also show that the power consumption is much lower. I don't know how much lower, so go refer to those papers if what you're interested in is a spiking ResNet. But for the PNP SNN that we deal with, where is the power? This is not the power yet, this is the accuracy. Okay, this is just showing that our PNP SNN have lower accuracy because of these hardware constraints that we're talking about. It's not a constraint in the algorithm, it's a constraint in the hardware. But generally, it's along the same trajectory, so I'm not going to dwell too much on this. If there's any gap in the accuracy, it's due to the hardware constraints, not to the spiking neural network design. So power, we compared our implementation on Loihi with an embedded CPU. I think it's whatever ARM CPU they have on the Jetson Orin. And we're talking about 100 times difference. 100 times difference in power draw. And runtime is in the same order of magnitude. The Loihi will be slower because you have to remember that it's a more primitive hardware compared against a state-of-the-art ARM CPU. But definitely in terms of power, we're looking at 100 times difference. And we're trying to convince. Any more questions on the results?
So what is the control in terms? You say the time is different and also the power. What is the control variable for the power conversion?
What is a control variable? Performance is this. The embedded CPU is just the gold standard, right? So the accuracy is slightly lower for the spiking version.
It's more like comparing two equal paths, not like, say, have a control variable, like not to have the same performance, same condition.
Yep.
And then you compare the power. Because you just show the result.
So the difference in the accuracy. So your point is excellent, but we are limited by Intel Loihi. It's not a very capable CPU. Sorry, it's not a very capable processor, and but this is not a limitation of our algorithm. Our algorithm, when we simulate it on CPU, it has the same accuracy. You get what I mean?
Okay.
Right? To fix these technological gaps in Intel Loihi is not an engineering problem, it's a commercial problem. That's up to Intel to, if it wants to give it a bigger instruction set, give it a floating point precision rather than integer, right? It's not a technological gap, it's a commercial question. Okay, so yes, our accuracy is lower, but we're limited by the hardware. Okay, so if the gap is not, the technology is equivalent, then the accuracy will be similar. And we believe the power gap, the power draw difference will still be there. Okay, we're not hardware designers, we're algorithm designers, and therefore we can only work with the hardware we're given. But excellent question. Okay, so a few more words on hardware readiness, because satellite engineers will eventually ask me this. Yeah, great concept, I like this. You know, is it space ready? On the way there, so our industry partner, Infinity Avionics, has this product. And we're procuring one now as we speak, which is a neuromorphic sensor for space application. And also a company called BrainChip, for example, has a space-ready neuromorphic implementation, neuromorphic chip implementation. Not space-proven yet, as far as I know, but, you know, and even on the left-hand side, it's also not space-proven yet, but efforts are underway. So that's mostly the end of the talk, but shamelessly, I would like to plug our upcoming events. This is the AI for Space workshop that Rajat mentioned at the beginning. I don't think this is released yet. I was taking this from the staging website, but it's a workshop at CVPR this year. So welcome to join us and submit papers. The other one I'd like to plug for is the SPICE event organized by ESA. I'm one of the technical program committee members. It's also AI for space, but a different way, different publication emphasis. The AI for Space workshop is more standard AI, peer-reviewed, 8 pages. This one is more 4 pages, a little bit more than an abstract, not so much emphasis on big results, big data sets, but more of a symposium to bring people together. And thank you very much for your attention.
Thanks, TJ, for the great talk. We are open for questions, so if you have any questions, we'd like to.
For the compute, have you considered using like FPGAs or to instead replace off-the-shelf accelerators?
What would be the benefit of FPGA?
It's like they customize. It's something that or rather, it's FPGAs right now are being used to implement neural networks.
Yep.
And so it also is more low power, since it's also the whole idea is the whole acceleration part. So I think it might be able to meet your needs, and like basically low power and also faster than traditional CPUs.
I don't agree with all of that, because we are working on FPGAs as well. At the beginning, I showed you a few missions that we are contracted to deliver, and some of them require us to look into FPGAs. They're not necessarily faster. They're not necessarily faster than a simple ARM CPU. Maybe the power is better. But the part I dislike the most about FPGA is the software development. Very, very challenging to change your algorithm and immediately transfer it to the FPGA. Very difficult. So maybe it has advantages in 1 or 2 dimensions, but there are other dimensions that count against it.
One last question.
I'm actually wondering, like, you always say, like, software side is okay. So I'm wondering, like, how do you see about, is there any limitation on this kind of somehow bio-inspired spiking neural network? Is there any limitation you found of it? Like, now you see it's very similar performance, super energy saving, but do you have any thoughts on the limitation? Just software side.
You mean the neuromorphic approach? Good question. Maybe there are like if you take a standard, maybe a state-of-the-art, a SOTA deep network, maybe let's say an LLM, and you're trying to do an SNN equivalent. Maybe there are operations that are very useful in the DNN that an SNN cannot perform. There are no equivalent processes.
So it's not the idea, it's more about to replace the existing engineering approach of the neural networks by the spiking.
There are several approaches. There's several major paradigms. One is to take a well-established ANN or DNN and convert it to the equivalent SNN. One is to train the SNN from scratch. It's still unclear which one is a better approach. And maybe they will never, ever be equivalent in terms of accuracy.
But the energy very efficient.
The energy is very efficient for sure, yes. Energy is definitely very efficient, yeah. But I think you can't win something without losing something. In the process of gaining that energy efficiency, you might lose something. And I'm personally hypothesizing that there are, or while guessing that there are operations that you do with a GPU that you cannot ever do with a neuromorphic chip. But I don't know what that is. Yeah.
Okay, let's thank TJ for coming here for our distinguished, as a distinguished speaker for the NUS Robotics seminar. Unfortunately, we've completely run out of time. I see that there are still few questions. Yeah, thanks, TJ.
Thank you, Rajat. Feel free to reach out to me if you have other questions.